everybody, and welcome back to Coding Fridays. Wait for me. Today we'll be talking about something that might seem tricky, but it is super powerful. Recursions in Python. Recursion is when a function calls itself in order to solve smaller parts of a bigger problem. Sounds confusing? Don't worry, I will break it down to you with simple and fun examples to make it all click. Grab your coding editor and dive into the world of recursion. Let's get started. Recursion in Python. Coding Friday. Wait for me. The topic is recursion. Recursion is a very interesting, sometimes it can get confusing for some students, but I'm going to explain it to you. I wrote some detailed notes in the Jupyter notebook, so when you're going through the notebook, you're able to remember some of the things that I said today. So recursion is a programming technique where a function calls itself in order to solve a problem. So we'll be calling the function inside the function. Usually when you define a function, you usually call the function at the end of the function. But in recursion, you're calling the function inside of it. So, and why do you do this? Is because you want to solve problems by breaking them into smaller sub-problems of the same time. So when you have to do the same thing over and over and over again, recursion, that's when you use recursion in Python. So how does recursion work? In recursion, you have to have a base case and a recursive case. A base case is the condition that stops the recursion to prevent an infinite loop. That's something that we also talk about in while loop, that you always have to have a point when you stop so it doesn't keep running forever. While a recursive case is when it's a case when the function calls itself within a smaller or a simpler part. So we will be using two examples. That is the factorial formula, and I have a really huge picture here for factorial formula, and also the Fibonacci series. So this is kind of like the best example using recursion, but there are so many other examples you can use. So I'll go through the step one by one. I wrote down the steps here. We'll define the base case. We said the base case, we don't want our recursion to run to infinity, so we have to put a condition to stop it. And then we'll define our recursive case. That is, we're calling the function on itself in a smaller part, and we'll call the function recursively with updated parameters. So the parameters you use to define the function at the beginning might be different from the one that you're using when you're doing the recursion, when you're calling it again. So we have to add the updated parameters to it. And the condition recursion will continue until it reaches the base case. Base case, the condition that says stop, do not go further. And then the function starts returning the result back up to the cost stack. So a reminder of factorial formula, factorial, if you do not remember, if you have a number, 1 factorial, that is simply 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And 4 factorial, 4 times 3 times 2 times 1. And goes on and on. 100 factorial will be 99, 98 times, and go on and on. And it goes on and on and on. So if you want to do this using recursion in Python, first let's define our function. Our function will just be define factorial n, and n is like the number, maybe 5 factorial, and so on and so forth. And then what we want to do is that if n is equal to 0, we want to return 1. And return 1 will be our base case. So as n continues to run, as it continues to multiply, once it gets to 0, that is, after it gets to 0, we want it to stop. That is our base case. So I'd have if n equals to 0. If n is equal to 0, I want it to return 1. So for instance, if you have factorial of 5, we'll do 5 times factorial of 4, 4 times factorial of 3, 3 times factorial of 2, 2 times factorial of 1, and then 1 times factorial of 0. And then when we get to the factorial of 0, it equals to 1. And then that is our base case. That means we're saying stop at that point. And then what is our recursive case? Because we're using, look at this, 2. What is 2 factorial? 2 multiplied by 1 factorial. What is our 1 factorial? Our 1 factorial is equal to 1. 3. what is our 3 factorial? Our 3 factorial is 3 multiplied. This 2 times 1 is the same thing as our 2 factorial. So 3 multiplied by 2 factorial. Our 4 factorial is what? 4 multiplied by our 3 factorial. And then you can break it then down to 4 times 3 times 2 times 1 and so on and so forth. So then we have to have our recursive case. So if we have, for instance, 3 factorial, we will then have 3. And 3 is then multiplied by, this 3 minus 1, that is 2, multiplied by the factorial of 2. Let me write the return statement so you can see it. So this is what we're returning. Let me write what I mean. So n multiplied by factorial n minus 1. So for instance, if we have 4 that would equal to 4 multiplied by factorial n minus 1. What is our n? Our n is 4. 4 minus 1, that is 3. So that would just be factorial 3. And that is just what this is. Factorial 3 is what? 3 times 2 times 1. So this is what our return statement is just doing. Now we have our 4, which is our n, and then we're multiplying it, subtracting n minus 1, and then we're calling our factorial on that again. And it keeps going on and on. So then let's now call our function outside the function. And then if I run this, I should get 120. So it starts from 5. It checks if is n equal to 0. No. And then it now performs this formula. It has 5 here. 5 multiplied by the factorial of 5 minus 1, which is 4. And then it continues until it gets to the point when n is 0, and then it returns 1, and then it stops. So this is how we're able to use recursion using the factorial formula. This is our function, and it is called here with a different parameter than what we have here. This is our base case, which is the point where we want our function to stop running, so it doesn't run to infinity. When n gets to 0, then we want it to return 1. And then this is our recursive function. We keep calling this ever till we get to n equals to 0, and then we return 1. So this is how we're able to do recursion using factorial. So now to the Fibonacci series. So Fibonacci series is quite simple. We'll first start from 0 plus 1. I don't have 0 plus 1 in this picture, but 0 plus 1 equal to 1. And then we'll then have 1 plus 1 equal to 2. I'm sure you can already see a pattern. Then 1 plus 2 equals to 3. And then we take 2 plus 3 equals to 5. And then we have 3 plus 5. It goes on and on and on. So you see, like, the second value added to your results to give you the next value. So you see here we have 89. You have here 55 plus 89 equals to 144. And then the next iteration will then be 89 plus 144 equals to 233. So this goes on and on and on. And if we want to do this in recursion, we would have our base case and would also have our recursive case. So in this instance, we're going to have 2 base cases. That is, if our n is equal to 0, we want to return 0. And if our n is equal to 1, we want to return 1. So this is my formula. So first, if n is equal to 0, we want to return 0. If n equals to 1, we want to return 1. Otherwise, we're doing this Fibonacci n minus 1 plus Fibonacci n minus 2. So we defined our function. This defines the Fibonacci function, and it takes n as the input, and it returns the nth Fibonacci number. And then if our n is then 0, we're returning 0 because this will match our f of 0. F of 0 is going to be 0 because sometimes they start from 0, other times they start from 1. But I'm starting my sequence from 1 here. But in the formula, just in case you're also starting from 0, you can have this: if n equals to 0, return 0. And then if n equals to 1, we're returning 1 because it matches the Fibonacci sequence. This is the Fibonacci sequence. You see, f of 1 is equal to 1. And then what we're not doing is that if it's not 0 and if it's not 1, we're using the formula. That is the Fibonacci n minus 1. That is the previous Fibonacci number. So for instance, if our number is, let's say here for instance 6, we'll then count 1, 2, 3, 4, 5, 6. We'll then take our n plus 1, that is our previous Fibonacci number, which is 5, and then our Fibonacci n plus 2, that is our second previous Fibonacci number, which is then 3. So for instance, f of 5 would then be f of 4 plus f of 3, and f of 4 would then be f of 3 plus f plus 2, and it goes on and on like that. So 1, 2, 3, 4, 5, our 6 is 8. So our f of 1, 2, 3, 4, 5, 6, 6 is 8. Our f of 5 is 5, and our f of 4 is 3. And that's how we're able to compute that. So now let me call our function with that Fibonacci. I hope I'm pronouncing it correctly, because I hope I know 6. And then we have that it is 8. So you see, we're able to call our Fibonacci, we're able to call it twice in our function using 2 different parameters. So we keep calling it again until we get our answer. And see, our Fibonacci of 6 is 8. 1, 2, 3, 4, 5, 6. If I do of 8, it's 21. 6, 7, 8. So it's just to get the number that we have here. And how we're able to do it is by using the formula and adding them together. Thank you so much for watching. And as always, the link to the notebook is in the description. Let me know if you have any question, and I'll see you next week for another Coding Friday with Fumi. Bye for now.